press the bell icon on the YouTube app and never miss another update.
Hello students, in the last class we are discussing about expression for current density. We have derived Ohm's law, discussed Ohm's law and its applications, right? And we have also discussed about resistance of a conductor. It is the opposition offered by the conductor for the flow of electric current through it. A conductor offers resistance, right, due to the collision of free electrons moving under the influence of external electric field with the vibrating heavy positive ions. That is the origin of resistance in a conductor. Now, resistance of a conductor is defined as the ratio of potential difference across the ends of the conductor to current flowing through it, right? And the SI unit of the electrical resistance is ohm. Now, resistance of a conductor is said to be 1 ohm when a potential difference of 1 volt across the conductor produces a current of 1 ampere in it, right? Now, let us take the factors on which resistance of a conductor depends. Right. Now, we have, right, resistance of conductor. Resistance is given by, we have R is equal to rho into L by A, where rho is resistance, L is length and A is area of cross section. But rho is equal to m by n e square tau, where n is free electron density, E is charge of electron, tau is relaxation time and m is mass of the electron, right? So that into L by A. This is the expression for resistance of a conductor in microscopic level. Right. Now, from this equation, right, now resistance depends on, right, number one, length of conductor, that is L. Number two, area of cross section of conductor, that is A. Third one, nature of material of conductor, right, that is N, free electron density of material. It is constant for a given material and different for different material. Now, fourth one, it depends upon temperature of conductor, that is T. Now, there is no term temperature in this equation, but among these terms, right, which represent the expression for, right, resistance, this relaxation time depends upon temperature. In fact, relaxation time is inversely proportional to temperature of the conductor. Therefore, as temperature changes, relaxation time changes. Consequently, resistance of the conductor changes, right? It is because tau is inversely proportional to T, that is temperature. These are all the four factors on which the resistance of a conductor decreases. That means, right, we can change the resistance of a conductor by changing the length, by changing the area of cross section, by changing material of the conductor, and by changing temperature of the conductor. These are all the four factors. Right. Now, another quantity which we are using in the study of electric current is conductance, denoted by the symbol G. Conductance of a conductor is the ability of the conductor to allow electric charges to pass through them, right? And conductance of a conductor is defined as the reciprocal of its resistance, right? Therefore, we have conductance is equal to 1 by resistance, right? Or mathematically we can write G is equal to 1 by R, where R is a resistance of the conductor. Now its SI unit is mho, writing reverse order of ohm because it is reciprocal, or it is represented by ohm inverse, or it is called Siemens. It is the SI unit of electrical resistance. That's all about the conductance. Just what is conductance, how it is defined, and what are the different units we can measure the conductance. But generally, this resistance is rather important than the conductor. Now, we'll take ohmic and non-ohmic devices. Right. Now, the electrical and electronic devices are classified into two types. One is ohmic devices and the other one is non-ohmic devices. Taking this ohmic device, the devices which obey Ohm's law are called ohmic devices, right? Now, the devices which obey Ohm's law are called ohmic devices. For example, so all metals, copper, aluminium, silver, gold, etc. Alloys like constantan, manganine, nichrome, etc. Right. Now devices like galvanometer, right, ammeter, device used to measure current, volt meter, rheostat, resistance boxes, resistance coils, every device which is made up of generally, right, metallic conductors or right alloy conductors or right ohmic devices, right. Now here for ohmic device, right, so this V by I is equal to constant, the ratio of current to potential difference to current is always constant, right. In other words, current is directly proportional to the potential difference. As potential difference is gradually increased, right, the current also increases, right. For different values of potential difference we will obtain different values of right current, but for any value of potential difference and current, V by I always remains constant. Actually this V by I is equal to constant is the basic Ohm's law. I is proportional to V or V by I is equal to constant, right. When we plot a graph of right voltage, that is potential difference against current, we will obtain a graph like this by taking potential difference along x-axis, current along x-axis and potential difference along y-axis, that is V against I, right. We will obtain a straight line curve for ohmic devices which is passing through the origin, right. Now the graph is a straight line passing through origin, right. Now if we take the slope of this graph, right, slope of the graph, say A, B, C, this AB represents, right, the change in potential difference delta V. This BC represents the change in current delta I. Now the slope of the graph now slope of VI curve, slope of VI curve, that is slope is equal to tan theta, that is AB by BC. What is this? AB represents delta V, the change in right potential difference. CB represents delta I, that is the change in current. Now this ratio of change in voltage to change in current represents what? Resistance. Therefore right here the slope of Vi curve is equal to resistance of the conductor, and this can be taken to be R. Now sometimes we will plot a graph of current against potential difference, right? So we can have two graphs, potential difference against current or current against potential. Let us see what happens when we take a graph of current against potential difference. Now, so graph of VI, V, that is I against V. When we plot a graph of I against V, we will obtain a curve like this. Now again we will obtain a straight line here. So that means this graph is also straight line for ohmic device. This graph is also a straight line for ohmic devices. When we take the slope of this graph A, B, C, here AB represents change in current delta I, BC represents change in potential difference delta V. Now the slope of IV curve, the slope of IV curve is equal to now this is tan theta AB by BC, that is equal to delta I by delta V is equal to 1 by R. Therefore, in this case, slope of IV curve is equal to 1 by resistance, or resistance is equal to 1 by slope, So generally we can plot I against V or V against I. In both the cases we will obtain a straight line passing through the origin that represents this slope always remain constant. That means V by I is always equal to constant. Now but here in case of previous V against I, directly the slope represents resistance, but in IV graph the reciprocal of the slope represents resistance. Now we are having two types of graphs, therefore don't get confused here. Now, why ohmic devices obey Ohm's law? V by I, that is R, is always equal to constant for a given device, It is because resistance of ohmic device is independent of potential difference and its polarity, That means here we have a resistance R, Now we have connected it to a battery. VB the potential difference and I is the current through. So if we go on increasing V, I also increases, It is because of the fact that we know that, though R is equal to V by I is a measurement of resistance. In fact, this resistance is independent of potential difference and we can say the current, because resistance depends upon only 4 factors: length, area, nature of the material and temperature. Now the R remains the same. Now this is AB resistance. If we change the polarity, when we change the polarity, the direction of current changes, but V by I remains same. Therefore, for any ohmic devices that obeys Ohm's law, resistance is independent of the applied value of potential difference and the polarity of the potential difference, Here the changing polarity means here A is connected to positive terminal, B is connected to negative terminal. The change in polarity means reversing the polarity, A is connected to negative terminal, B is connected to positive terminal. When we change the polarity, there is no change in the magnitude of current, but there is a change in direction of current, and resistance is independent of change in direction of current. It depends only on 4 factors, Therefore, ohmic devices, they obey Ohm's law. Now, non-ohmic devices. The devices which do not obey Ohm's law are called non-ohmic devices. The devices which do not obey Ohm's law are called non-ohmic devices. Now, we take example. Generally, electrolyte like copper sulfate, discharge tube. When a gas taken in a tube at low pressure is applied a potential difference, electric current flows through it. That is due to ionization of the molecules of the gas. Remember the concept of the dielectric strength and dielectric breakdown, When the applied electric field or potential difference to an insulator or dielectric exceeds the dielectric strength, dielectric breakdown takes place, electrons are released, positive ions are also released. Now it starts behaving as a conductor. But the discharge tube, where electricity can be discharged through gas at low pressure, does not obey Ohm's law. Now, semiconductors, germanium, silicon, and oxides of metals, semiconductor diode or junction diode, semiconductor transistor diode wall, right? Earlier, before the discovery of semiconductor, we are using tube electrons where the diode wall is used. Now we are using semiconductor diode, that is PN junction. Now triode wall, right, etc. are non-ohmic devices. They do not obey Ohm's law, right? Now here for non-ohmic devices, right, V by I is not equal to constant, right? So V by I is not equal to constant, right? That means when V by I is constant, that means the device obeys Ohm's law. When V by I is not equal to constant, and as we go on changing the potential difference, current also changes. For different values of V, corresponding I, V by I is not constant, right? V by I is different for different set of right, potential differences. Therefore, they do not obey Ohm's law, right? When we plot a graph of current against voltage, I will take here for semiconductor diode in forward bias. Semiconductor diode in forward bias, I will obtain a curve like this. This is potential difference taken along x-axis, the current taken along y-axis. We will obtain a non-linear curve, right? When we obtain non-linear curve, the slope is not constant. It is different at different point on the curve. That indicates that V by I is equal to not constant. So in this case, if we take the slope, right, ABC. So here AB represents change in current delta I, BC represents change in voltage delta V. Here resistance is equal to, right, 1 by slope, that is equal to BC by AB, that is equal to delta V by delta I. Now for different ohmic devices, the nature of curve may be different, but I have taken a particular case, right? I have taken a semiconductor diode, a junction diode or a PN junction in forward biased condition, right? If I change the polarity, right, then it is called reverse bias. Then the nature of curve will be different. Right. Now the question is, why non-ohmic devices do not obey Ohm's law? Why V by I is not equal to constant? It is because of the fact that in case of non-ohmic devices, resistance of the device depends upon the value of potential difference as well as polarity of the potential difference. Therefore, as we change the magnitude of potential difference, there is a change in current, but resistance also changes along with the change in potential difference. At the same time, right, when we change the polarity also, then also there will be a change in the value of resistance of the non-ohmic devices. For example, we will take a semiconductor. When we take a semiconductor diode, PN junction, when P is connected to positive terminal, N is connected to negative terminal, it is said to be in forward biased condition. In forward biased condition, a current flows through the junction diode, right? It conducts current and offers a right relatively low resistance, right? Now, when it is reverse biased, that means P region is connected to negative terminal, N region is connected to positive terminal, right? Very, very negligibly small current of the order of 10 power minus 6 flows through the right diode. For high value of potential difference, low value of current is flowing through this, right? And this indicates that the resistance is right very high, relatively high during reverse biased condition, right? So a junction diode conducts current only during forward biased condition because of low resistance. It does not allow current during reverse biased condition. It offers some high resistance. That means to say, resistance of non-ohmic devices depend upon the applied potential difference and its polarity. Right. Non-ohmic devices do not obey Ohm's law because their resistance depends on value of applied potential difference and its polarity, right? Generally, when we take a transistor, right, a semiconductor transistor having 3 terminals, right, having 2 junctions, one junction is forward biased and the other junction is reverse biased, right? So that is the reason why non-ohmic devices do not obey Ohm's law. Right here, interestingly, right, R is equal to V by I holds good for both ohmic and non-ohmic devices. See it here. Though we have derived R is equal to V by I from Ohm's law, but this R is equal to V by I, this equation is the definition of right electrical resistance. By measuring potential difference and current through a device, we can able to measure its resistance, right? So this equation is used to measure resistance of both right ohmic and non-ohmic device. Only the difference is, for every value of V, R remains constant for ohmic devices, but for different values of V, R will be different and R is not constant in case of non-ohmic devices. Now we will take another concept, resistivity or specific resistance, rho. Now experimentally, for example, say, right, by plotting graph of current against potential difference for a conductor, by changing the length, by changing the material, by changing the area, by changing the temperature, it is found that resistance of a conductor, given conductor, is directly proportional to length of the conductor, right? That means the resistance of a conductor increases with increase in length, right? Secondly, resistance of a conductor is inversely proportional to area of cross section of the conductor. When we increase the area of cross section of the conductor, right, now, right, the electrical resistance of the conductor decreases, right? Now, so experimentally, it is found that so resistance of a conductor is, number one, directly proportional to length of the conductor. Length of the conductor, that is, R is directly proportional to length. Number two, right, it is inversely proportional to area of cross section of conductor. These experiments are, right, at constant temperature. While doing these experiments, the changing length, changing area, right, so we kept temperature constant. That means R is inversely proportional to, right, area of cross section, right? Now that R mathematically is directly proportional to length and inversely proportional to area of cross section, or R is equal to rho into L by A. Actually, we have derived the same equation while deriving Ohm's law, where R is equal to rho L by A, but experimentally also we get R is equal to rho into L by A. Here what is rho? Here rho is, right, called resistivity or specific resistance of material of conductor. Resistivity of material of the conductor, right? That means it is constant for a given material and it is different for different materials. Now, from this equation, we have resistivity rho is equal to, right, R into A by L, right. R is equal to, rho is equal to R into A by L. So when, right, L is equal to, right, 1 meter, that is unit length. A is equal to 1 meter square. A unit area of cross section. Then, so rho is numerically equal to R. The word is the value of R is equal to the value of rho. That doesn't mean that resistivity is equal to, right, resistance of the conductor. That is, here resistivity is numerically equal to resistance. Resistivity is numerically equal to resistance, right? So when resistivity is numerically equal to resistance, right, when we take a conductor of unit length and unit area of cross section, right, the resistance offered by a conductor of unit length and unit area of cross section is numerically equal to resistivity at constant temperature. Therefore, we can define rho. Definition of resistivity. Right. Listen. Resistivity of the material of a conductor is defined as resistance offered by the conductor per unit length or unit area of cross section of the conductor provided temperature is constant, right. So resistivity, right, resistivity of the material of a conductor, right, is defined as the resistance offered by the conductor of unit length and unit area of cross section at constant temperature. That is the definition of resistivity. Generally, this will ask in a board examination for 1 mark. These are defined resistivity or specific resistance, right? Now, SI unit of resistivity is equal to, right, SI unit of resistance, that is ohm, into SI unit of meter area, that is meter square, divided by SI unit of length, that is meter, right, that is equal to ohm meter. It is equal to ohm meter. So, SI unit of resistivity is ohm meter. Resistivity and resistance are two different physical quantity. Of course, they are related, right? Resistance depends upon resistivity, but resistivity is independent of resistance. Now we'll take some important points regarding resistivity. So number one, we have resistivity rho is equal to, right, R into A by L. So number two, for a cylindrical wire of length L, comma, radius R or diameter D, having resistance R, then we have resistivity rho is equal to pi R square capital R by L, where R is radius of the cylindrical wire. It is because area of cross section of a cylindrical wire is pi R square. Or in terms of diameter, rho is equal to pi d square R by 4L. It is because in terms of diameter, A is equal to pi, right? R is equal to diameter by 2, D by 2. R is equal to D by 2 whole square, that is equal to pi D square by 4, right? So if we know radius, resistance and length, we can calculate resistivity using this equation. And there is an experiment to determine resistivity of the material of given conductor, right, in practical classes, where we are going to use rho is equal to pi R square R by L, where resistance is measured using a device called as meter bridge. Radius can be measured using a screw gauge, and length L can be measured using a meter scale, right? So in terms of diameter, we are having this equation pi d square R by 4L. And third one, we have, right, resistivity rho is equal to m by n e square tau. M by n e square tau, where m is mass of electron, n is free electron density of the material, e is charge of electron, tau is a relaxation time. Right. Now from this equation, right, the resistivity, right, resistivity of a material depends on, number one, depends upon, number one, here m constant, e constant, generally constant. Number one, nature of material, that is rho is inversely proportional to n, right? Now if the free electron density of a material is more, then its resistivity is less. If the free electron density is less, then the resistivity is more. And second one, it depends upon, so temperature of material. Here right? Rho is inversely proportional to tau, and tau is inversely proportional to temperature, right? Therefore, resistivity is directly proportional to temperature, right? Resistivity of the material increases with the increase in temperature. Now, the fourth one, in terms of mobility of electron, right? We have rho is equal to m n e square by tau. We have mu e is equal to e tau by m. It is the expression for mobility. So this can be written as this is tau divided by, right, m by e. Mu e is equal to tau divided by m by e. Therefore, we have rho is equal to, we can write it is 1 over this n e by m, taking this one mass, into tau. What is this term? Right? This is straight away we can take this one, no problem. Right. So now this term e by m into tau, it represents mobility. Therefore, rho is equal to 1 by n e mu e. This is the expression for resistivity of the material of a conductor in terms of mobility of electron. Now, fourth one and very important, right? Resistivity rho of a material is independent of its length L and area of cross section E. It does not depend upon its length L and area, right? It is because resistivity is the rate at which, right, the material offers resistance or opposition. Resistivity is the resistance per unit length per unit area of cross section, right? For example, when we are going to a textile shop purchasing cloth material, when we say how much this is in a thon, not piece, shirt piece, in a thon, right? Now he say that, sir, it is 500 rupees. It doesn't mean that he will give the entire roll for 500 rupees. His means 500 rupees per meter. It is the rate. And different cloth material will have different material. Some cloth material may have 100 rupees per meter, right? Just like it is the rate, resistivity. But resistance is the amount of cloth what you take. For 500 rupees, if you take 2 meter, it costs 1000. So 3 meter, 1500. So if you take it 1 meter, 2 meter, 3 meter or 10 meter, rate remains the same, 500 rupee per meter. But how much dimension you take, the resistance changes, right? Suppose you take 100 rupee per meter, for 2 meter it costs 200, for 3 meter it costs, right, 300, right? Similarly, when we take, say, it is a copper piece, right, having certain length, certain area, depending upon the resistivity, right, it has a resistance R is equal to, right, rho into L by A. Here resistivity remains the same. Suppose if we stretch that wire, when we stretch that wire, there will be increase in length, right? Consequently, area decreases, right? When there is a change in length, change in area, right, the resistance value changes. Suppose if L dash is the new length, A dash is the new area, then new resistance R dash is equal to rho into L dash by A dash. That means resistivity rho is same in both the cases, right? Because it is both the cases, it is a copper only, right? But as length changes, area changes, resistance of the conductor changes. Therefore, resistance of a conductor depends upon its length and area. For a given wire, by changing the length, by changing the area, we can change the resistance, but the resistivity remains the same, right? So here, right, we can write resistance is property of, right, conductor or object, right? Whereas resistivity is property of material. Generally, when we go to the shops, the cotton cloths cost more, the terracotta cloth cost less. Generally, we will say that when we show the cloth to, so this somebody says this a good material is good. Somebody says that the material is not good, right? So generally, when the material is good, shirt is same, cotton shirt or terracotta shirt. But depending upon the material, its rate depends, right? Similarly, depending upon the material, resistivity depends, but resistance depends upon length and area of cross section of the material of the conductor, right? So generally, we use metal alloys like nichrome, manganine, constantan, right, as a resistance wire or resistance coil. It is because of the fact that the resistivity of alloy is more than the resistivity of pure metal or the constituent of the material. So if the resistivity is high, we can use less length, right, so that it can occupy a small space in a device. Therefore, right, here resistance wire or coils are made of alloys such as, right, nichrome, manganite and constantine, right? Now generally the resistivity of alloy is greater than the resistivity of right, pure metal or constituent metals, right? Now generally for pure metals resistivity is low, right? Generally the among the metal the silver has the lowest, right, resistivity, and it is always the best conductor, right? Now resistivity of silver, it is equal to 1.6 into 10 raised to the power of minus 8 ohm meter. It is followed by copper. The resistivity of copper, it is equal to 1.7 into 10 raised to the power of minus 8 ohm meter. Now resistivity of aluminum is equal to 2.7 into 10 power minus 8 ohm meter. Resistivity of nichrome, it is equal to 100 into 10 power minus 8 ohm meter. Now resistivity of manganite, it is equal to 44 into 10 power minus 8 ohm meter, and the resistivity of constantine is equal to 49 into 10 raised to the power of minus 8 ohm meter. So among the metals, right, silver has the lowest resistivity, highest conductivity, right? In general, right, this resistivity, when we compare conductors, semiconductors and insulators, right? Now resistivity of, right, insulator is greater than the resistivity of, right, semiconductor, which is greater than resistivity of, right, metallic conductors, right? This is of the order of 10 power 14 ohm meter, resistance of insulator. This is of the order of 10 raised to the power of 5 ohm meter, like germanium, silicon, etc. It is of the order of 10 raised to the power of minus 8 ohm meter. So among the metals, silver has the highest resistivity. Now seventh one, for ideal conductor, resistivity is 0 for an ideal conductor, and of course that does not exist in reality, but we will consider when ideal conductor the resistivity is 0, right? And for ideal insulator, rho is infinite. For ideal conductor, right, resistivity is 0. For ideal insulator, resistivity is infinity, right? That's all about resistance and resistivity. You should have a clear idea regarding the concept of resistance and the concept of resistivity, right? When we go to the practical application of resistor, right, where we should have an idea how resistance of a conductor changes, right? And another thing is here why resistance of a conductor increases with increase in length. R is directly proportional to L. So, if we have two conductors of same area, right, but different length. Here this is L, this is L dash. This offers resistance R, this offers resistance R dash. Obviously, what is the cause for resistance? It is the collisions of free electrons with vibrating ion. Consequently, as the length increases, right, the number of collisions encountered by free electron, right, moving from one end to the other end of the conductor is more. That means obstruction is more, opposition is more, and resistance is more, right? So, as L is greater than L dash, that means R is greater than R dash. That's why resistance of a conductor is directly proportional to length of the conductor. Now, resistance is inversely proportional to area of cross section, right? We will take, right. Now this is area A, length L, resistance rho, and R is the resistance. We will take another one, right? Right, same rho, same length, but A dash, right? Smaller area of cross section, right? It will be R dash, right? Now, as A is greater than A dash, R is less than R dash. Here, it offers small resistance, it offers greater resistance. It is because here the electron will find more number of paths to flow from one end of the conductor to the other end. Here it finds less number of paths. Suppose we are having single road, double road, 4-lane highway, right? In which case a vehicles can move faster. Obviously 4-way line where there are number of paths, 4 paths. In a double line we are having only 2 paths for the movement of vehicle. In single line we are having only 1 path, right? Therefore, with increase in area of cross section, number of electrons, electrons find more number of paths to move from one end of the conductor to the other end. That reduces the number of collisions, thereby reducing the resistance of the conductor. Therefore, resistance of a conductor decreases with increasing area of cross section of a conductor.